Morning, everyone. So today I'll be talking about the effect of tidal interactions on the evolution of low mass galaxies. So we know that the evolution of galaxies, one of the main drivers of the evolution of galaxies is mergers or interactions. And these kind of interactions can be divided into mergers or flyby events. So mergers are actually when two galaxies collide, and in the case of flyby event, they just pass by kind of. And they can again be divided into classes like major event or a minor event based on the mass ratio of the interacting systems. If it is greater than 1:4, it is considered as a major event, and if it is less than 1:4, it is considered to be a minor interaction. So these events in high mass regime, when I say high mass, it's around 10 to the power of 10 solar mass, stellar mass greater than 10 to the power of 10 solar mass. These kind of events in high mass regime are relatively well studied, both observationally as well as theoretically. And what they say is that these interactions can induce morphological changes, such as disk galaxies be converted to ellipticals, like to spheroids, and the stellar and gaseous streams around the galaxies. Then they can trigger star formation, and they can induce gas inflows leading to nuclear starburst or AGN activity. So all these kinds of things can be induced in mergers for the higher stellar mass. But these kind of studies, the effect of these kind of interactions on low mass galaxies are less understood. Low mass in the sense less than 10 to the power of 9 solar mass of stellar mass. Then why do we care about dwarf galaxies? Because they are important regardless of redshift. They dominate the population, galaxy population in the universe. And according to hierarchical galaxy formation model, we expect these interactions to be scale-free, and you expect interactions in lower mass regime. And majority of the mergers at all redshifts are expected to be for low mass galaxies. So because of all these reasons, the effect of interactions on the evolution of low mass galaxies are important. And can we just extrapolate the results that we get from the high mass galaxies to low mass galaxies? It may not be possible because like dwarf galaxies are low mass systems, hence low tidal effect. So we really don't know whether these kind of interactions can essentially induce star formation, morphological changes, and drive gas inflows as we see in the high mass end. And also they are prone to environmental effects than massive galaxies. So because of these, like we need to have a separate study of dwarf galaxies to understand their effect. We cannot simply extrapolate what we see in high mass. Yes.
So just a general point, so interaction between dwarf galaxies will not affect them as much as interaction between a dwarf and a giant galaxy, right? Because
yes, so when you have like basically what we are trying to look at dwarf interactions means low mass interacting low mass galaxies. But if these low mass galaxies are actually a satellite of a massive galaxy, then we cannot disentangle, and that actually dominates the. So if we really want to understand the effect of low mass galaxies, we need to go to a low density region where there is no massive neighbor, and it is actually just two dwarfs or little dwarfs.
so it is that I was wondering whether two dwarf galaxies would be like looking at two similar mass galaxies, or in some ways that is like a major.
Okay. So no. So that is relative to these masses. But what I meant is like massive, like a really giant galaxy nearby can completely change the scenario. Okay, so why these studies were limited due to the challenges in detecting these galaxies and substructures around them, and significant theoretical challenges as well in this, because simulating large enough volumes to provide a realistic cosmological context while simultaneously resolving these to the dwarf regime was not very, right now there are a lot of progress, but there are challenges. And as I was just telling, these dwarf interacting systems, there are like satellite systems. There are many. So, and most of these studies focused on individual systems. So, for example, Magellanic system, which is one of the nearest interacting system, they are the Large Magellanic Cloud and the Small Magellanic Cloud. They are dwarf galaxies and they are interacting, and you can see the signatures of interaction in H1. This pink is H1, and they are satellites of Milky Way. And this detailed study of these systems have shown that these kind of interactions can enhance star formation, create substructures like warps, and all these things. But then the thing is that, as I mentioned, these are the neighbors of Milky Way, which is a massive galaxy. Then it is difficult to disentangle the contribution of the massive neighbor and on this dwarf-dwarf interaction. So dwarf galaxies being highly susceptible to environment, the satellite groups are imperfect probes. We cannot actually use them as probe to understand the dwarf-dwarf interactions as such. Okay, so. But then there are isolated dwarf-dwarf interacting systems. So here, these people have found out clearest evidence of hierarchical structure formation at low masses using deep multi-wavelength data. This is from Magellan telescope. So they have identified 7 isolated spectroscopically confirmed group of dwarf galaxies. So they do exist like dwarf galaxies or groups which are in isolation from massive systems. So the study of these kind of systems are essential to understand the effect of dwarf interactions. Okay, so there are studies again related to individual systems mostly. So there's MGC 4490 and MGC 4485. This is an isolated analog of the Magellanic system. There are recent studies on that which try to understand the dwarf interactions on their evolution. But many of these are again the DDU 68 and other studies with these are all based on individual systems. People are trying to understand the effect of interactions on dwarfs galaxies. But when you come to large statistical studies, many of the panchromatic surveys which study dwarf galaxies do not focus especially on this aspect, the effect of interactions between dwarf galaxies on their evolution. But right now there are a lot of surveys coming up. So there are like many surveys coming up and which are ongoing as well to understand these effects, mostly in the local volume and in the mass range of 10 to the power 9 solar masses, which CFHT, Subaru and LBT. And there are also other studies coming up. So all these, like they look at the resolved stars because they are in the local volume, so within a few megaparsec, 3 to 10 megaparsec, and they try to understand their star formation history based on the resolved stellar population analysis. And there are, along with these surveys, there are also improved simulations now, which allows to understand the theory in the dwarf regime, which can be compared with the observations. So based on these results, these are some of the interesting results. So this group, they found an enhancement in star formation rates by a factor of 2.3 in the isolated pair dwarfs over isolated single dwarfs. And one of the interacting systems, so here this is Adeno 1647 plus 21, they found enhanced star formation in the sample. So they did the MUSE survey, IFU survey, and found that this star formation is widespread and clumpy in contrast to merging massive galaxies where the gas funneling leads to nuclear starbursts. So there are like a lot of recent studies in this area. Some other, this is like a deep Subaru observations where they have found tidal features like around the low mass galaxies, and then they correlate with the star formation activity from the H alpha observation. So then basically it says that so if what they found is there are like tidal features around dwarf galaxies, like it's not just a companion, just the tidal features. So that suggests it might have gone to a merger in the past. So those kind of galaxies have a higher star formation rate, which is correlated with their. So that's an evidence of like the effect of these things on star formation. But there are also studies which did not find enhancement in star formation of the interacting dwarf with respect to local volume. And there was a recent paper which looked at this using the large binocular telescope. They looked at this galaxy NGC 3741, where they found extended star formation and young bar-like feature in the dwarf galaxies, which corresponds to the H1 bar, which they previously have identified in this. So these are like interesting things, and which they connected to the context of recent merger or ongoing gas accretion. So finding a bar in the young bar is interesting. So there are studies. So most of these studies are in optical and are on galaxies with stellar mass around 10 to the power 9 solar mass, which is basically the upper end of the low mass regime. and they lack dedicated UV studies of these systems to understand the star formation in different environments. So in this context, we started a UV study of a sample of nearby interacting dwarf galaxies in this mass regime in low density environment. By the long-term goals for this project is basically to understand the interacting systems to reflect on star formation rate, their spatial distribution, to identify tidal tails, and combining with multi-wavelength data, characterize these star-forming clumps and compare with simulation, and also compare with diverse environments, not just the isolated region, but also with fields, galaxy groups, and clusters, so that how these properties vary. So in this part, I'll be mainly talking about the dwarf of interactions in void region. So voids are low density regions in the cosmic, the filament, you see cosmic filaments, etc. So you see low dense region, these are called voids. There are presence of low mass galaxy in void region. Though majority of the dwarf galaxies in the voids are isolated, there are many studies which show that around 20% of galaxies are either in pairs or triplet. And it also provides this isolated dwarf galaxies can be used as a control sample. So then these kind of systems, which are metal poor and gas rich, interacting dwarf systems are like analogous to small high redshift system, which form the basis of the hierarchical assembly processes.
Was there any particular reason why you wanted to look at a void region?
Okay, I'll come to it. These are you don't have any neighbor. They are very sparsely populated, and you don't have a massive neighbor nearby if you want to select. So I'll come to it. So what we have done is we have looked at a lens cancer void region, which is around 80 megaparsec from us. So based on the optical catalog, we have identified 58 dwarf galaxies, and based on this catalog, they have done the isolation parameter, and there is no massive galaxies with the 3D volume of 2 megaparsecs. So you can clearly differentiate, rule out any contribution from a massive system to these galaxies. So there are 22 interacting systems identified either based on their interacting nature, based on H1 map. So this is a system UGC 3672, which is observed using GMRT by Jairam and his group. So they have found a common envelope connecting this dwarf system, and we can see that there's regions in the galaxy majors as well. So these are either based on H1 maps or using or by perturbation indications of perturbed morphology in the optical images. These systems have been selected in this catalog. We have just taken that, and there are 36 isolated single dwarfs. So what we have done is we used initially did the study using Galax data. So so this is the one of the galaxies. So this magenta circle here is the ellipse here is the optical ellipse based on the optical radii and the ellipticity. But if you see like in UV, they are clumpy and there is no regular structure. So we used a Python package called AstroDendro, which identifies the clumpy structures in the galaxies, and the largest structure corresponding to the galaxy is considered as the galaxy. So we also overplotted. So here you can see this is the structure, and we estimated the integrated flux for UV flux and estimated the star formation rate using the standard calculation. So this stellar mass for all these galaxies are also available, which are estimated based on their integrated optical magnitudes using mass luminosity color relation. So here we have just corrected. So just note that we have corrected only for the foreground extinction. We have not considered the internal extinction for these galaxies. Okay, so what we found is that, so here, this is the stellar mass versus star formation rate plot. So this points in the different colors are for the different mass range. So 6 to 7 are in this orange. These violet points are from 7 to 8, 10 to the power of 7 and 10 to the power of 8, and these green points are from 10 to the power of 8 to 10 to the power of 9. And these open circles are isolated sample, and open stars are interacting systems. And this black star and circle are the median values for different mass range, because we have to compare the star formation rate for a particular mass range for the similar mass range. So what we see is that majority of the sample here, we have like enough sample in this particular mass range, 10 to the power of 7 to 10 to the power of 8 stellar mass. So here we do see some kind of enhancement in star formation rate. So if you zoom in, this is what we see. There is around 5 times the enhanced star formation in interacting dwarfs compared to the isolated dwarf systems. And this actually matches with some of the recent simulations where they predict that the dwarf-dwarf interactions drive moderate increase in star formation rate in low and intermediate redshift, that is 2 to 4 times. So these are comparable. So this is one of the results we got. And then so here the sample is actually less, so we cannot actually divide that based on their different you mean dwarf galaxy morphologies, right? Yeah, so that we have not done because the sample itself is less big, and also we have not considered at what stage of interaction they are, like whether the pair are like what distance. So those factors will be interesting to consider. But if you want to do that, we should have a large statistical sample at different the pairs at different distances, different morphology, and so mass ratio, all these things to be considered. You need a larger sample. So here it is just this. It's difficult to separate it out into different. Okay, so then all the studies were based on Galaxy observations. Now coming to UVLT. UVLT, as you all know, has a better resolution compared to Galaxy. So that enables to understand the spatial distribution of star-forming clumps and the propagation of star-formation. So this is a UVLT image of one of the interacting systems. So this is the zoom inversion. This is compared to Galaxy. You can see the improvement in resolution. So in this context, we proposed based on the study from the previous study, we proposed larger observations, like for a larger number of galaxies, 10 interacting dwarfs and 6 isolated dwarfs using far UV observations using UVLT. And we also have complementary optical data from Gemini as well as 3.6 meter optical telescope. And here I would like to mention that this UVLT study is suitable for nearby dwarf galaxies, comparison of star formation in dwarf galaxies of different morphology, what you asked, like not based on interactions, just based on being studied by a group at IA, like you can visit see Amrita's poster. So based on this, we have selected, like we are still getting.
Sorry, that last point related to the last point. Are the dwarf galaxies in void similar to what we see in the field? In the sense of mass distribution?
We have similar masses, but we don't know about the star formation rate and comparisons. Yeah. So this is Maushmi's student Amrita. She is working on it. There is a poster there. Yeah, okay. So from the sample, we have one system, like two systems taken, UGC 5272 and UGC 3600. This work is done by Renu as part of a coursework project. Why we chose this is like this system, like this is an interacting system and this is a control thing because you can see that they have a similar stellar mass. So we can compare at least the 5272 with UGC 3600. So this is the H1 contour plotted over the H alpha observations or the R band observations. So you can see that this is 5272, this is the main galaxy and this is the interacting, and they are connected with H1, overlapping H1 contours. So which suggests that there is an interaction, and this is the UVLT field of view with these two galaxies identified. This is one of the deepest UV observations for this system. Okay, so this is again these systems taken from the large field. What we have done is, in the earlier, we did a single structure for this galaxy. Now we can identify subclumps based on the same astronomical tool. We have identified around 228 clumps in this system and around 18 members. And here you can see that in this direction where you have the H1 contour overlapping. There are some star-forming regions, but we need more investigation to conclusively say anything about this. But there's effective radii of this, like each clump has a very irregular shape. You can take the area of that and equivalent circular area. You can just say what is the effective radii. This is around 35 to 180 parsec. Larger clumps are in the central. When you go to outskirts, the clump sizes are smaller. And we also check for the star formation rate of these clumps. We can see that this is the color scale here compared to the main galaxy. This is 5272 and UGC 3600. You can see there is an order of magnitude difference, so relatively order of magnitude difference in the star formation rate of the clumps. And but the star formation rate, when you take from this, it's also dependent on the clump size. So we need to remove that bias by calculating the star formation rate density. So here also you can see that the if you see the scale, they have a larger star formation rate density compared to this one. So this is interacting and this is isolated. So this could be due to the tidal interaction of this system. So these are some preliminary results from this study. Okay, so in the future will be to do it for a larger sample and combine it with deep optical imaging so that you can characterize the star forming clumps and also the optical images can be used to understand the older population morphology of the system and then compare also with this is for the voids, so you compare it with larger different environments. And spectroscopic studies of bright star forming clumps and combining with H1 and looking at the morphology will be interesting. So in the context of this meeting, I put 2 slides on this dwarf galaxies in the era of MSc and PMT. So the main thing is the MSc surveys focus on the local volume, the representative volume of the local universe in the MSc surveys is basically to go to the low stellar mass and the main science drivers for that is the dwarf galaxy interactions in the low stellar mass regime, environmental effect, etc. So you need a more low to moderate spectral resolution, and there are surveys in this, and the fundamental measurement will be the extension of the stellar mass function below 10 to the power of 8 solar mass and with a complete spectroscopic sample. So these are the parameters taken from this MSc detailed science case document, chapter 7, where these regions, if you see, this is the limit now up to around 10 to the power of 8, which is from the gamma observations. And now with MSc, we will have for a lower masses with larger numbers, we can have this spectroscopic identification of groups and the velocity dispersions, etc. for this, and probably with some chemical metallicity information also. And with the second generation IFU, you can map these systems and see how the parameters change across the galaxy. And these are the parameters if you compare with the SDSs, which is up to R less than 17, up to 17.8. The MSc surveys is aiming for I band around 23 to 24.5, which will cover most of the local universe dwarf galaxies less than 10 to the power of 8 solar mass. And you can have follow-up observations with extremely large telescopes like TMT. And in the case of SK, I'm not a radio astronomer, so I don't know much, but what I found interesting from the SK document is that this is, if you have a very high spatial resolution and low column density sensitivity, you can do this H1 mapping for a sub-kiloparsec. And then, because what I understand, and also compare what is the connection between the star formation on small scale with the global scaling relations like the Koenig-Schmidt relation. Like you normally do it for, as far as I understand, we are limited with the H1 resolution. So probably with SK, we can go to the resolution under which we are actually observing this UV clumps, etc. So that can be compared. So that will be an interesting project. And so basically this is the take home, and I'll just leave the slide.
Thanks, Smitha.
So my question is regarding the dendrogram analysis. So there could be hierarchical structures, right? Yes. Instead of just clumps. So how do you take care of that? Plus, so how do you identify the smallest possible clumps?
It is limited by your PSF size. So that is the smallest clump. So PSF decides that. And
it will be equal to the PSF.
The smallest clump will be equal to the PSF, but I have not marked it, but you identify all the smallest structure and the hierarchical structure up to the largest structure. All these things can be like, if you are talking about branches and all, right? So all those are identified here, but the clumps that I've shown are like from sizes of the PSF to a size where it cannot be split based on the dendrogram analysis.
So these are the basic structures. Okay. You also have to put a limit on SNR.
You showed a picture, plot earlier of star formation rate and log stellar mass. So that's the main sequence, star formation main sequence, but yours is the dwarfs. How does it compare to that for main galaxies?
I have not compared the slope. Basically, you are saying if it to this line and compare with the SMR. I have not done it. It will be an interesting thing to do.
Yeah.
Smitha, can you show a couple of slides later? Yeah, no, this is the one before that. Yeah, what was this about actually? Oh, your identifying the system. I'm just intrigued by your comparing the raw galaxy being wide compared to normal, field galaxies, and I'm not sure how comparable.
No, I'm not comparing with the field
No, I'm not
galaxy.
comparing. I mean, I would like somebody to compare.
Yeah. How? So that is what. So the idea. So one of the goals is like at the later stage, you do it at different environments, like from galaxy clusters to groups and balls. So that'll be an interesting thing.
Yeah, I am from a really old era, so I remember listening to a talk in the US once when the first galaxy star forming was found in void, and it was a big excitement and this.
So in general, this void galaxy based on H alpha observations, if I remember correctly, there is an enhanced star formation in voids compared to the field.
This is regarding star formation density. No, you had a star. Yeah, okay. So this is like more than 10 times it.
Around 6, around 6 times for the same similar stellar mass. This is slightly higher if I say like 3.4 and this is 1.7 or something.
Okay, so what is the typical star formation density you see in spiral galaxies or galaxies, for example? I mean, does it enhance quite a bit?
Enhancement in star formation rate.
Star formation is divided for.
The range.
Yeah.
I was checking that yesterday, but I couldn't actually compare it properly with it. It varies actually. I don't know exactly the numbers, but I couldn't find.
I'm just wondering because some of these things lead to kind of quite a bit of star formation efficiency in the sense that.
So that actually
you cannot create return spiral galaxies. So does it exceed this?
Okay. That part I didn't. I was actually comparing with the star formation rate density from the galaxies. Some clumps are identified in galaxies, which are the largest clump sizes, right, based on the resolution, and then compare the clumps in that particular clump, smaller clumps. So what I found is, like as you said, like it depends on like how smaller scales you go and then find. But it will be interesting to check with the masses. Yeah, that I.
Okay, last question, Dilakara. I think my question related to what there and the Puni has described. These two galaxies, the right one, I don't know what is the gas content of that. The lower star formation is because there is no gas in that.
Or it is, yeah. So
how can you say that it is because of interaction?
Correct. So there is like a single dish H1 observations for this, and the stellar to gas ratio is similar. Stellar mass to gas mass is similar. Yeah, it's all similar in the sense, not exactly, but yeah, but the order is same. But that is based on a single dish observation of H1 mass, which is available in the literature.
Okay, there's no further question. Let us thank the speaker, Smitha.
Long live India and France friendship.